All right, this is it, day 25, the final problem from Advent of Code 2022. This one is actually fairly short. Once you really wrap your head around it, you'll see that as we get into the code, but it still was a little bit challenging to figure out exactly what to do. So it took me a couple hours to figure this out, but let's get into the problem. You may have heard of binary, octal, hexadecimal, all these different number systems. You may have even heard of ternary, just different ways of writing digits, but you have probably not heard of a balanced quinary. So we have base 5, but instead of different numbers being 0, 1, 2, 3, 4, it's 0, 1, 2, negative 1 being this minus, and equals being minus 2, negative 2. So we have to first take this list of numbers and translate it into decimal. That is quite easy. But then we have to take a large decimal number. We have to add all of our inputs together, and we have to construct the new number in balanced quinary. So that they call it snafu. That's sort of just their name for quinary. But we have to reconvert it, and so our final answer has to be in balanced quinary. So how do we do this? Let's go into our code. Parsing is fairly straightforward. We just have these lists of these numbers. So really, parsing a single line is just a matter of parsing, some of these different characters, and we just associate each character with a number. We're just going to go straight to integers. So we have, 2, 1, 0, negative 1, negative 2. Very, very simple. Now, translating a snafunum, that is a quinary number, into an integer is also pretty easy. We do the same basic thing you would do with binary. We zip our numbers together with their index. So notice we reverse this, zip it with 0 to 1, and then we fold out with this adding function. So we have the index and the number. We take 5 to the power of that index, multiply it by the number, and we add that to the previous value. This gives us our decimal representation of each of the input snafu numbers. We take the sum of those, and that's sort of the first part of the problem. And now in the second part, we have to translate that number back into quinary. We have to take the sum and translate it back. And this part is a little complicated. Really, all of the work is done by this function, decimal to snafu tail. It's a recursive function. It's not, properly speaking, a tail recursive function, which is because of this case. We'll get to this case eventually, but let's talk about the inputs to this function. So we have our remainder. So this is the value of our input that we still have to calculate, that we still have to translate into those quinary numbers. Now we also have a cum. This is the list of integers, the digits that we have already translated. And finally, we have power 5. This is the next greatest power of 5 that is larger than our current remainder. So if we go back into this function, I calculate first power 5 by creating a list comprehension. I look for all of the different powers of 5, and I just take the first one head of all of those where n is greater than our input number. And this is helpful because it tells us what we are doing on the current digit. So the first case is our base case. If the remainder, if its absolute value is less than 3, we just have one digit remaining. We just, append that value onto our accumulated list, and we reverse the list, and that's our final result. Base case out of the way. Now we have all of these other cases, and I'll start by describing what this case is. So we can imagine different thresholds of, how big is our remainder compared to the next power of 5. The first case, the difficult case, comes when our remainder is greater than half of that next power of 5, because this is how we'll actually introduce these negative values into our definition. This actually involves carrying, but we'll talk about that in a second. First, I want to talk about the other cases because those are simpler to understand. So we can imagine considering our remaining value compared to the next power of 5. If it's greater than 50%, then we have to go into this strange case. Now, if it's between 40 and 50% of that next value, we have this case. So we are greater than or equal to 2 times the next 5. And next 5 in this case, I've taken our power of 5 and I've divided it by 5. So if we're greater than twice that, then we're in this 40 to 50% threshold. And in that case, we just append a 2. We know that we are placing a 2 for our quinary number here, and we are appending that to our accumulated list. We are subtracting 2 times that next 5 value from our remainder, and then we are recursing. So the next 5 becomes power 5 in the next iteration of this function, and we perform the subtraction and we'll recurse. The next case, very similar, except now we're dealing with 20% to 40%. So remainder here is greater than or equal to power 5 quad 5. I could actually have just substituted next 5 there. I don't know why I did that. But anyways, we place a 1 in the accumulation, just as we placed a 2 before there. Now we place a 1. And in the otherwise case, so now we're dealing with more or less 0 to 20%. In that case, we're appending a 0. So in this case, our number is less than a fifth of the next greatest power of 5. So we actually don't do anything. We just place a 0 there. It's a placeholder digit. And then we go into this recursive call. So that is all of the cases but one, fairly easy to understand. What happens here? Now, if our remainder is greater than half of the next power of 5, then we actually have to do a carry value. And carrying in the sense of addition, where you add 2 of the digits together, they're more than 10, and so you carry the 1. And that's basically what's happening here. You might wonder, where do we introduce negative numbers into our value? Because all of the numbers we've introduced in these cases are, non-negative. And this actually happens through this case. We need to carry a 1, and then the recursive call we make is with the same power of 5, but we take the power of 5, subtract the remainder, and then at the end of that process, after we've gotten this recursive result for our translated function, we need to reverse the add 1. So what is add 1? We take our previous accumulated value, and we carry a 1 into it. So we take the head of that value, we add 1 to it, and we append that to the tail, and then we reverse it, and then we append the negative result of this recursion. It's really hard to explain this without having paper in front of me, but I'll try to talk through one example. Imagine we have a number that is 60% of our next power of 5. So like our next power of 5 is 125, and we're talking about the number 72. What we have to do is carry a 1 into the next position, and then take 125 minus 72, so that's something like 53. And then the following recursive call will be in something like this case, probably. So it is guaranteed to not fall into this case once again, and we will get a normal number, but we have to reverse all of the values in that number by doing this step. It's kind of weird, but it works. And I also had to spend a lot of time convincing myself that there was never going to be a chained carry. If we have to carry this, we are guaranteed that the head of this is not a 2. And it just sort of works out that way, because if we have this 40% case here, I think it just works out. Again, hard to explain without having pen and paper in front of me, but this is the code we need. Like I said, it's not properly tail recursive because we do our tail call and then we do more actions here, but it still kind of follows the pattern. Once we have our final list of integers, obviously it's very easy to convert the integers back into the snafu characters, and so we return our final string. And that is basically the end of the problem. Here was the string I get. There's not a part 2 of this problem, because for the last problem in Advent of Code, the last part of the final day 25 is always just validating that you have gotten all of the previous stars, and then you get your 50th star. That is just so that the leaderboard works out, so that whoever gets this final star first is the true winner who has completed all the problems. So I hope you have enjoyed this long series of videos on Advent of Code. I hope this has helped you to improve your problem-solving skills with Haskell. I hope you've seen some techniques you hadn't thought about before, especially with how to use folds and recursion and state patterns. These are the most common things I've seen in these problems, and just, graph algorithms are also obviously very important. So I hope you appreciated these videos. If you did, make sure to subscribe to our YouTube channel, subscribe to the Monday Morning Haskell mailing list, and always remember that you can look in the video description for the source code on all these Advent of Code problems, as well as links to the blog write-up. So thank you so much for watching.